This video is part of the lecture for multivariable calculus, and I'm going to solve 3 examples of how to do double integrals over rectangles. So let me start by example 1. Okay, so I have the double integral of x minus 4y cubed dA over this region, and I'm gonna set up the integral first. So I'm gonna say that this is equal to the integral of, I'm gonna do dx first. When I do dx first, I need to write the bounds for dx on the inner integral 0 to 2, so don't forget to write the correct bound. And then for dy, it's on the outer integral, so I'm gonna write the bounds here. So when I have the integral with respect to dx, I assume that when I want to solve the inner integral, I assume that y is a constant. Y is fixed, y is a constant. So I'm gonna write the outer integral 0 to 1, and then I'm gonna take the integral of this function with respect to x, assuming that y is constant. So with respect to x, I get x squared over 2 minus, this is a constant, with respect to x, the antiderivative would be like that. And then I'm gonna write x from 0 to x equals to 2. Don't forget to write the variable in here. It's just because it's important that when we want to use the fundamental theorem of calculus, we don't actually plug in, for example, 0 to for y in here, which would make everything very wrong. So 0 to 1, I'm gonna plug in 2 in here, so it would be 4 over 2 minus 4y cubed 2 minus plug in 0, which would be 0 minus 0 in here, and then dy. So what do I get? Let me have more space. So on here I get the integral from 0 to 1 of 2 minus 8y cubed dy. So you see that the answer for the inner integral, since y is a constant, it would be a function of y. Okay, and now I'm taking the integral of that with respect to just y. So it's just a simple single integral. It would be 8 over 4y to the fourth. Y is from 0 to y equals to 1. Plug in 1, I get 2 minus 2 minus plug in 0, I get 0. So the answer for this integral is 0. Okay, let's go to the second question. I'm gonna solve this integral in here. So I'm gonna set up the integrals first. So I have the integral, let me do dx first. So I'm gonna write the bounds for x in here of the function for x minus 2x sine y. And then I'm gonna do dy, so bounds for the y. I'm gonna keep writing the outer integral, and then for the integral, inside integral, I'm gonna take the integral with respect to x. It would be 2x squared minus x squared sine y. Okay, and then x is from 0 to x equals to 1. Let me bring dy a little closer. So I have the integral, plug in 1 for any x, it would be 2 minus plug in 1 in here, sine y, minus plug in 0 in here, 0, plug in 0 in here, 0, and then dy. So I have a function of y, I'm gonna do dy, so it would be 2y minus cosine of y, and another minus, so it would be plus cosine of y. And then y from 0 to y equals to 2, so plug in 2 for plus cosine of 2 minus plug in 0, I get a 0 plus cosine of 0. Cosine of 0 is just 1, so this is 4 minus 1, which is 3 plus cosine of 2. That's the answer for the second integral. Now, let me do the third example. I'm gonna set up the integral first. So I'm gonna do y e to the xy. Let's do dy here. Dy dx, I'm gonna put the bounds for y here, which would be 0 and 3. Okay, the bounds, pay attention to the bounds. And then dx, I'm gonna put the bounds for dx in here. Now let me integrate the inner integral. So for the inner integral, if I want to integrate, I have a function of y in here, I have another function of y in here. So I need to do by parts in here and then solve it. So it's a little hard using by parts. Okay, so now instead of doing that, let me change the order of integration. Am I allowed to do that? By Fubini's theorem, yes. It's just because I have a continuous function in here, which is just a polynomial y, and then I have exponential function, which is continuous, and then I have the product of two continuous functions. So when our integrand is continuous, by Fubini's theorem, we are allowed to change the order of integration over rectangles. So I can change the bounds. I'm gonna write y e to the xy. I'm gonna write dx first now, and then dy. So when I do dx first, the bounds would be 0 to 2, and then for dy would be 0 to 3. Now, does this make any difference? Let's see. I have 0 to 3, and then dy. Look at the integral in here, the inside integral. For the inside integral, let me erase this one. It's just because we are taking integral with respect to x, so y is constant. So for example, you have 5e to the 5x. You see? It's so easy, right? So the antiderivative of this function with respect to x would be what? Would be y is the constant, I write that, and then the integral in here would be x to the y divided by y. You see, it's just because exactly I have this situation. Erase this one. So now I have x from 0 to x equals to 2. Let me bring this one a little closer. And so I have 0 to 3 e to the xy, x from 0, x equals to 2 dy, which would be what? Plug in 2y, minus plug in 0, it would be e to the 0, and then dy. E to the 0 is basically 1. Now let's integrate with respect to y. I get e to the 2y divided by 2 minus the integral of 1 is just y. And then y is from 0 to y equals to 3. So plug in 3, I get e to the 6 divided by 2 minus 3 minus plug in 0, I get e to the 0 divided by 2 minus 0. I mean, as you see here, I just get a 1/2. So don't assume that when we have 0, it would be 0 everywhere. Just plug in and make sure that you do all the steps. So it would be e to the 6 divided by 2 minus 3 minus 1/2, which would be negative 7/2.